Okay, so announcements here. So standard comments and then some comments about the final project. So Money's Point, of course, due this Sunday. There is the second concept check from this unit. It's not due this Sunday. It's due the Sunday at the end of spring break. So spring break, I think, next week. Then there's mini project 3. So I usually try to give you roughly a week after the concept checks to get the mini projects done. And that's due the Sunday after that Sunday. So that's supposed to be a week between these here. Now the Saturday before that, that's when this member election. So some people have already submitted this, but this final project, which kicks into gear after spring break. The idea here is to choose to find one other person in the class to team up with. If you go to the final project module in Canvas, there is a Google Sheet that I've shared that's meant to be kind of a clearinghouse for if you're having trouble finding someone, then maybe you don't come to class and you don't want to post something, you don't know a lot of other people in the class. Of course, you can post something to Slack, post something to Ed discussion or the discussion boards. But another option is this sheet where if you don't know anyone else in the class, if you go to that sheet, just add your name and some contact info, then anyone else who comes to there can reach out. So add your name to the sheet and then come back to the sheet, because some people might just add their name but forget to reach out. But if you come back, you might see somebody else has added their name and you could reach out to them. So that usually helps facilitate making these pairings. Having two people per team does help with the peer review. It helps to ensure that we get multiple eyes on each submission. So I know that there's some students that might, and it also just helps with grading. It makes the grading of these things, which I tried to make them not that much of a burden for you with these final reports only being 4 pages and then a 10-minute presentation. But still, if we were to allow 40 students to do that, all of those individually, then it really makes it difficult to get all of that grading done in that last week. So 2-person teams, not 3, not 1, due to the number of students in the class. I think there are an even number, but still there's always a chance that there might be some slack things to be taken up. So it is possible that there might end up being one group that doesn't match this 2-person template, but that's the idea there. So of the 40% of your grade or something that the final project is responsible for, that's all divided up into a bunch of smaller assignments. And this team elections one is one of those. So it's pretty much just easy points where you just submit your name and your partner's name. They do the same thing, so I can confirm there's agreement, and then I'll add you to a group in Canvas so that then the rest of the assignments can be submitted as a group instead of individually. All right, any questions about that? Okay, so this is kind of where we've been. We've been talking about multi-objective optimization. And so we had to define what that meant in general, and then we sort of suggested that because evolutionary algorithms use populations, those populations are natural representations of sets. And so they have sort of a natural affinity for multi-objective optimization. If we can just figure out the right fitness concepts in order to drive that population so that it produces a set and not just an individual solution. So there are classical methods that we talked about that do that, like Vega and random weight GA. Those show that it was possible to produce Pareto frontiers through evolutionary algorithms. But they didn't spread out very uniformly over the Pareto frontier. They often would cluster near single objectives. And if you had these non-convexities or concavities in a Pareto frontier, then these early methods completely missed those. So what we started talking about last time was a new innovation in fitness, or at least a newer at that time, this Pareto ranking approach, which rather than trying to come up with random trade-offs among objectives, those random weightings of objectives, then it kind of gets rid of the weightings completely and tries to develop a fitness concept that's based on distance to the Pareto frontier. And then once you're at the Pareto frontier, then it worries about spreading things out. So, and that is going to introduce these niching methods, which become important to the next unit as well. Okay, so this kind of gives us an opportunity to talk about the community ecology of multi-objective optimization. I just use the term niching. You know, it kind of comes from thinking about communities in nature. So in nature, there is no one objective. Like it would be wrong to say that natural selection is trying to optimize intelligence or optimize speed or anything like that. All natural selection is trying to do is trying to increase fitness, trying to increase reproductive success. And how you get to reproductive success can differ based on different trait combinations, different trade-offs. And so, you know, when we think about it, so I think it's just like it's sort of, I think, probably bad to sell optimization in high schools as a way to find a single best solution by setting a derivative equal to 0. You also don't want to market natural selection as looking for the one, you know, true best body plan or something like that. Natural selection is about finding different ways to achieve reproductive success. And those different ways are these so-called niches. And so we have, if you go into any forest, you know, if you go into any urban environment, you're going to have a community of different organisms which are coexisting. They do not compete with each other. So that idea of coexistence sort of shows that they live in some sort of equivalence class where they're all doing just as well. So they all are relatively high fitness for their selective pressures. And yet they're not competitively excluding each other because they have different trade-offs. They have different traits. The one that has, you know, the one that is more is faster, like a sloth can coexist with some high-speed predator. And those two have very different strategies, but they both exist in the same habitat, in the same environment, with the same selective pressures because they trade off different objectives differently. And so when we refer to niches, we refer to different balances, different trade-offs. So that's what I'm kind of depicting here. You've got these multiple objectives, objective 1, objective 2. You can think of those as characters or traits. So there's different ways you can mix your traits. And so each one of these dots is a different mixture of a trait. But if you've mixed your traits in such a way that you're down here, then it is possible for selection to find other trait combinations which dominate that trait combination. And if it happens to find some of those, then you will be crowded out fitness-wise. You know, these will have higher fitness than you because they are objectively better than you. They are better in all possible ways. And so this one will eventually go away over time, and then these will be selected for, but then each one of those can be dominated by other trait combinations and so on until you hit the Pareto frontier. And then these individuals, they don't have any who can dominate them. But if there happen to be a couple of individuals that are close by, then they can you know, sort of micro-dominate them. They can exclude them. So within each one of these bubbles, we have this competitive exclusion, which is a term we use for saying that in a community, there's only going to be one member, typically speaking, for every niche. And so there's an exclusion. Those who, if you're most efficient for living in that niche, then you're probably going to crowd out anyone else who's the only thing they got going for them is that niche. And so within each niche, you only get a single member. But then if those members who aren't as good at that niche find a way to move into another niche, then they can coexist in that other niche. And and then it reduces the competition, and so that allows for the coexistence of multiple niches. So that's where we get the term niche. It's sort of a mixture of different trade-offs, a mixture of different traits that prevents competition, that allows for sort of an equivalence class of high fitness solutions that can coexist. And we present these high fitness solutions to our stakeholder, and our stakeholder will say, actually, I really only care about objective 2. And so, okay, that's fine. Well, then we're going to choose this design for you. They say, I only care about objective 1. Well, that's fine. We'll choose this one for you. So we've managed to summarize for them the top F2 and the top F1 designs. But if they look at that and they say, well, based on, I actually do like both of these objectives, and based on this trade-off here, I actually like this objective a little bit more than this objective. So I'm willing to sort of I'm willing to take a certain hit in this objective in order to get a certain gain in this objective. And so when they look at all of the possibilities, then they might say, actually, this is the ideal design for that. So this gives them kind of a buffet of possible designs to choose from, where any one of these you could say is not a feasible solution. These are all bad solutions because all of these should be eliminated because there are ways to do better in both objectives that we think the stakeholder cares about. But in this case, it really is a trade-off. It really is a choice of going from one to the other. You give up one thing in order to gain another. So that's our community ecology of multi-objective optimization. And what we would like to reproduce is this idea that reproductive success is a generic movement toward the Pareto frontier, as opposed to in the older ways that you did multi-objective optimization, you just agreed to a random weighting. So it's like you agreed to this direction, and you tried to find individuals that were better and better in this direction, and then you found a spot on the Pareto frontier. And then you chose another random direction, and you found another spot and another random direction. So each one of these were sub-problems that you maximized one at a time. And so you needed to make sure you had a good coverage across the space to do these sub-problems. Here we're doing it a very different way, where we're just saying generically we were going to put a pressure that is in the direction of the frontier, and then hopefully as we're moving toward the frontier, we're going to try to additionally penalize clustering and amplify diversity so that we eventually spread out along this frontier. Yep.
Is there like a specific hyperparameter for like kind of determining the size of the niche?
Yes, we're going to see that. So when we start with Pareto ranking, and then very quickly we're going to go into these diversity preservation or so-called niching methods, and the niching methods have exactly what you're saying. So you have to sort of decide that I don't want niches to be any bigger or any, like I'm going to try, roughly they're going to be this size. And then that is going to be an algorithmic mechanism to redistribute individuals that get too close. So in nature, that's a much softer boundary. In nature, it's going to be like, you're going to have specialists and generalists. And so there'll be like a generalist that is in an environment with no specialists may just, they may eat all the fruits. They may go to all of the flowers. But if they're in an area where there's a specialist for one of their flowers, and that specialist is so much better at exploiting that flower, exploiting that fruit, then the generalist may not have that in its diet. But that's okay because the generalist can survive on other things that the specialist doesn't care about. So in nature, these things are sort of self-organized, how big these niches are. But we are, in our engineered systems, we don't have quite as much complexity. So we have to enforce that by putting our own kind of hard boundaries into these mechanisms, which is exactly what we're going to talk about today. All right, another question about this general perspective about this idea that we have niches along a community that coexists. And those are our biological analogy for different trade-offs you can make in equally relevant designs. These are irrelevant designs. These are totally reasonable designs, defensible designs. Okay, so we talked about dominance ranking last time. So I introduced this idea of the dominance cone, which I don't know if anybody else calls it that, but it's this idea that if you have focus on an individual and you focus on an individual and you look, what is the positive direction? So, all of my examples I've been showing F1 is better to be good in both F1 and F2, but you could imagine that it might be better to be less in F1 but greater than F2, in which case the dominance cone would still go up here, but it would go down here. So these would be the ones that dominate this solution. So you have to look at what your reference directions are, and then you just project those reference directions onto a new little axis anchored at the point that you're considering, and you draw a little dominance cone. And so anything in this cone, anywhere in that cone, dominates this individual. And so that if there's nothing in this cone anywhere, for the infinity of options that are up here, then that we call a non-dominated solution. And if we've explored the whole space, then the set of non-dominated solutions we found are definitely in the Pareto frontier. The Pareto frontier is the class of non-dominated solutions, or the Pareto efficient set, I should say, is the class of non-dominated solutions. And they all live on the Pareto frontier in criteria space here. This is criteria space because we're plotting the criteria. Whereas these individuals down here, their dominance cones in this example all include one individual. So they are dominated by one individual. And that's bad, that's not great for them, but it's much worse to be this individual whose dominance cone includes all four. So this individual is sort of really bad because there's lots of options that are better than it. These individuals are kind of bad because there's one option that's better than them, and this one's pretty good. That said, if there are others that are further down and up the Pareto frontier, we'd like to find them. So we not only want to reward dominance, which would reward this individual, but we want to keep enough individuals around so that we have the opportunity to keep searching. So this green one might, evolve over time. It might mutate and change so that it gradually moves over in this direction so that eventually it becomes non-dominated. And so there might be an advantage to keeping this green one around. This one might just be so far gone that there's no value to keeping it around, because if you were to mutate it, the best you could do are the ones you already have in your portfolio. So that's what we want to induce with our Pareto ranking. So we talked about 3 different ways you could do that, which different algorithms have tried. So this SPEA is a multi-objective evolutionary algorithm. I don't care if you remember SPEA, but its approach to dominance ranking was to rank by the number of solutions found in the current generation that you dominate. So this high fitness one has a rank 4 because there are 4 that it dominates. It falls into 4 dominance cones. This group, this equivalence class, all have rank 1 because there's only 1 that they dominate. And this one here has rank 0 because it dominates none. Now, it's not great in an evolutionary algorithm to have a fitness of 0 because a lot of these early evolutionary algorithms depended on fitness proportional selection. And fitness proportional selection, 0 fitness values can be a problem for a number of reasons. So oftentimes you just add 1 to all of these. So instead of being 0, 1, and 4, it becomes 1, 2, and 5. All right, so that's one approach, by ranking by how many the focal solution dominates. The downside of that is it puts so much distance between a non-dominated solution and the kind of next tier of solutions that it creates a really high selective pressure for those that are currently the best estimates of the Pareto frontier, the best estimates of the non-dominated set. So it's great in that you very quickly can find non-dominated solutions, but you purge diversity from your system. And so it doesn't help you sweeping over the Pareto frontier. And you might prematurely assume that a solution is non-dominated, when in reality you just haven't done enough searching, and there might have been other individuals that would have fallen into this dominance cone if you had the diversity of other individuals to help explore that space. So this big gap can be a problem. An alternative then is to flip the ranking around and make fitness more of a minimization concept here, make it related to how many others dominate that individual. In that case, this top individual has none in its dominance cone or its dominion cone, so it gets a rank 0. So then the ones right behind it that only have it in their dominion cone, they're rank 1, only 1 dominates them, and then this one's rank 4. So the nice thing about this is that you get a compression of the difference between your high ranking solutions, your good solutions, and then you get a spreading out. So the selective pressure here might be doing something you like, where it's sort of, it helps ensure that these individuals stay around, and it puts a huge penalty on this individual so that its spot in the population can be given up so that you can have more exploration. So this is what MOEA, the Multi-Objective Genetic Algorithm, did. And there's some argument for why this might be what you want, but it still puts, it turns out that because Pareto ranking it's what I refer to, what you see in the literature as fitness degeneracy. So it means that it creates these classes of equal fitness solutions that is much higher than you'd expect in a normal genetic algorithm. Usually fitness is not so discrete. So you usually don't get a huge number of individuals with exactly the same fitness. And that creates problems for drift because now you have a lot of neutrality. And it's just generally, although it allows for diversity, it also doesn't promote diversity. And just so it's a double-edged sword. And so this high selective pressure, even when it's down here, can maybe be overkill because Pareto ranking, it's going to be so important to maintain diversity as you go to higher and higher ranks. So that is where NSGA2, which is sort of the dominant two-objective, multi-objective optimization algorithm, its approach comes from here. So this uses an iterative kind of Pareto peeling approach where you keep peeling off the non-dominated points, and then you rank them by what round they were peeled off. So in the first round, this is the only non-dominated point, so it gets rank 1. In the second round, after this is removed, these all become non-dominated. And so they then get peeled off in round 2. After you remove them, then this is the only one left over, and it's now non-dominated, so it gets rank 3. And the nice thing about this approach is it creates a dense rank. So when we talk about ranking mechanisms, even outside of evolutionary algorithms, we talk about sort of sparse ranking systems where you can have gaps and dense ranking systems. And this always produces a dense rank. There will be no gaps. And that sort of has the weakest selective pressure. It still has some selective pressure, but it doesn't put a huge gap in between levels that's kind of arbitrary, like some of the other ones do. All right, questions about those 3 methods? I can say this has become a very influential approach, this peeling method here.
Yeah, what's the difference between NSGA 1, 2, 3?
So we'll talk a little bit about that. But NSGA 1 was the first. NS is non-dominated sorting genetic algorithm. And so author, I think Deb is associated with NSGA. And so this is a class of non-dominated sorting genetic algorithms that all use this ranking technique. NSGA 1 used this ranking technique plus a very sort of inefficient diversity preservation method called fitness sharing that we're going to talk about here. NSGA 2 used a more efficient diversity preservation mode. It was much more practical. And in NSGA 3, but NSGA 1 and 2, the way they do fitness ranking, it turns out for 3 objectives, it kind of works, and 4 objectives, it just doesn't work very much at all. And that's because once you get to 4 objectives or higher, everything looks non-dominated. It's kind of like the same problem happened in history and social welfare with Pareto efficiency. When politicians or policy folks were to think about policies that would best benefit a society, on paper, if you said, well, if I have 3 individuals then if I can manage to benefit all three simultaneously, I should take that policy change. That's better for society. That works really well on paper when you only have 3 parties in your society. But once you have 1,000 parties in your society, like 1,000 objectives, it is really hard to find any Pareto improvements. Because it's just like, how are you going to find? You have 1,000 people with 1,000 different utility functions. And how are you going to find that one movement that makes it better for all of them simultaneously? Even if it exists, it's going to be a needle in a haystack. And that's what happens with an SGA 2. When you have 4 objectives or higher, it's really hard to, everything looks like it's non-dominated. Every point, it looks like you can't find, so they all get the same rank. And if they all get the same rank, you don't have any fitness pressure, and you aren't very effective at finding that Pareto frontier. So between an SGA 2 and an SGA 3, that MOEA/D that I mentioned before, that decomposition-based MOEA that is based on Chebyshev decomposition, showed a way to do decompositions with targets. And this is outside of the scope of the class, but if you're interested in this, I posted a video on this. But it showed a different way that you could kind of cut up the space ahead of time. And influenced by that, algorithms like NSGA 3 found new ways to still do dominance-based ranking, but to do it in a more guided way towards targets, which allowed you to make sure that you were exploring the whole space and not just hoping that Pareto ranking would manage to inflate the balloon to fill the whole space. Because Pareto ranking, you can make work in 2 objectives to kind of grow in a way and eventually hit that Pareto frontier. But once you're 3 or 4 or 5 directives, it's a little bit like, it's like a limp balloon, and like, you blow it up and you just get pockets. It doesn't fill until you get like a lot of individuals. And so in order to fill out the Pareto frontier with 4 objectives or more with an SGA 2, you need lots and lots of population, lots of individuals. In SGA 3, creates a scaffolding that allows you to better hit that Pareto frontier, even if you have lots and lots of objectives. So that's detail that we're going to develop as we go on here. But the point here is that in SGA, that family all uses at some level this iterative peeling. Any questions about this method ranking? All right, so this, you could theoretically use all 3. This has become a popular method. Regardless of the method, you can follow your choice of fitness with a fitness scaling operator, and many of these methods do. So they come up with a rank, and then they scale the rank to another space, which allows them to adjust their selective pressure even further, which is the same logic we've seen in many single objective canonical GAs. The idea that once you've calculated a simple fitness, then you can run it through a scaling algorithm to further shape it. But the more fundamental problem, which is I've talked about here, is fitness degeneracy creates a neutrality issue. And that now you have lots of individuals that all look neutral relative to each other. And so members of the non-dominant that have equal fitness, given that they're relatively neutral, then that could create an issue with drift if you're using a very drifty selection operator. But in general, it doesn't promote any diversity. So like, because they're neutral, even if you don't have to worry about, so drift will collapse them all to a point. But even without worrying about collapsing them to a point, if you are just using fitness to drive exploration, there's no reason to, like the perpendicular, you've been driven to the Pareto frontier, but once you're at the frontier, if all fitness is done, has driven you up to this frontier, then what is going to drive you left and right? That's the bigger issue. So elitism is an approach that can be used to prevent from losing individuals, so that'll help guard against drift, but how do we spread out? That's what we're trying to get to here. And this is where we're going to now, we want a new mechanism to add to Pareto ranking that operates in parallel with Pareto ranking, that penalizes clustering and promotes diversity. And this is that competitive exclusion. So if we find that everyone has arrived at the Pareto frontier at one point, like every individual just happens to have found itself here, then we're going to want to penalize that, create some exclusion so we can start spreading these ones out so they can find other points along the Pareto frontier instead. And that's what these so-called niching methods do. Okay, so we're going to go on now and switch to these niching methods and diversity preservation. Before I do that, any further questions about this Pareto ranking idea? Using dominance as a fitness driver. Okay. All right, so how do we preserve diversity in this niche or criteria space? So this is something we're going to get to in more detail in actually the back half of this lecture, depending on how the timing of this thing. But this is going to be really important for multimodal optimization as well. And so I'm not going to go into great detail on each one of these methods at this moment because we're going to get into them when we get to multimodal, but there basically are these 4 categories of niching methods. And so the first one I've already kind of mentioned is elitism or just general archival. So if you archive individuals in your non-dominated set, you prevent them from being lost, but then you can also use that archive to try to drive new exploration. Like we have a lot of individuals here, we're going to use that to drive new exploration in a new area there. So archival approaches are usually built in. A lot of times, some version of this, particularly elitism, is going to be added to these other methods. So I'm not going to go into a great deal about them. In multimodal, I'll bring up one approach, which is sort of very much like it uses a species conservation list. That will be involved here, but that'll become like at the very end of multimodal. And I'll use a niche as a term, but we're going to also see the term species come up. And that also goes along with this idea of community ecology. We don't think of those niches as being one species. We think of them as different species that have speciated in order to find their own way, different trait combinations. And the trait combinations are so different that we might as well call them a different species. In fact, we might even, in the case of MOEA-D, you only get recombination among very close species in trait space. If they're very far away, it doesn't even recombine them, they don't communicate at all. And that kind of goes along this idea of like, you've got the origin of these species that actually are really separate. There's no gene flow between them. Okay, the first and most common, or earliest form of niching was a fitness modification method. Both of these are methods that they achieve niching by once you have your baseline fitness, they then adjust the fitness in order to create additional pressure to not just reach the frontier, but spread out along it. And these are often computationally expensive because they require looking at where you are relative to where everyone else is, and then updating your fitness based on the density of others around you. So they require a lot of pairwise combinations or pairwise comparisons. So if you have 100 individuals, then for every individual to figure out how many individuals are around it, it has to end up iterating through all of the other individuals to see, are they close enough to degrade the fitness of this individual? So these fitness-based methods tend to be computationally expensive, which is why they end up kind of giving way to these other methods. But they're kind of the first thing people thought of. And the mascot for these is fitness sharing. So in fitness sharing, which I'll show you more detailed formulas for in multimodal, the idea here is you count, and this goes back, there was a question earlier about how big the niches are. For every individual, you calculate their fitness based on Pareto ranking, for example, and then you say how many individuals are within this sigma share, this radius of you. And then based on that, you divide your fitness by that number, assuming that the rest of those will have similar fitness to you, and they'll also be divided by that number. So it's kind of like if you have this this frontier, whatever you do, this community, and these, if you've got 3 individuals all in roughly the same space, then we're basically going to treat these as an entity that all receives the fitness, and then it gets split 3 ways among them. So we're saying this position on the Pareto frontier gets 9 offspring, and we're going to do 3 for this one, 3 for this one, and 3 for this one. Without fitness sharing, then you can get, all 3 of those might get 9 offspring because they all sit in the same spot, roughly speaking, in this sort of fitness space. But we're going to divide them down so that each one of them acts like it's far less fit, but then collectively as a group, they have the same fitness. So we're probably, that might end up, if we have 3 that are close together, that might end up killing off one of them. But that's okay, because the other 2 will stick around, and the space that's made for this one will now get redistributed and hopefully find another spot on the frontier. That's the idea behind fitness sharing, dividing individual fitness by a count of individuals around. It adds a density dependence to fitness. Questions about that? Now, so for fitness sharing, an alternative approach that does a very similar thing is fitness clearing. And so the idea here, and again, we'll see precise algorithms for this when we get to multimodal, but here the idea is if I've got those 3 individuals, rather than smoothly saying all of these get a certain fitness divided by 3, then what I might do is just take the top individual, so the slightly marginally better individual, or a random one of these 3, say it becomes the sole possessor of this niche, and I just set the fitness of the other 2 to 0. Just clear them out. So I just not kill everyone but a certain subset. And then their spots in the population get redistributed elsewhere. It's basically the same idea of using fitness in order to spread things out, but instead of doing it in a kind of smooth way, it's a little bit more harsher way, more discrete. Yeah.
What is distance?
Distance in genotype. So when I get to multimodal, I'll have this all written out in a little bit more formal way, but typically, it doesn't have to be, but typically in genotype space, it's like the distance, the L2 norm between 2 genotypes. So if you happen to both be Pareto rank 1, and your genotype is like a giant vector, and then someone else who's Pareto rank 1 has also got a genotype that's a giant vector, they're 2 numerical vectors, then I just define a genotype distance, which might just be like the L2 distance, like the distance formula distance between this vector and this vector. And if you're within this sigma share or this sigma clear, then you get hit by that effect. If you're far enough away from it, then you're not involved. All right, so then an alternative approach, so these again tend to be more costly because they involve a lot of pairwise calculations, comparisons. So an alternative approach is not to use fitness, but to jump straight to a more selection-based approach. And the kind of mascot for these are crowding methods. And again, we're going to get to multimodal. I probably should just get rid of this slide and just skip to multimodal. But this is like a summary of what's to come. And this, still sort of living in multi-objective here. Turns out a lot of the same niching methods in multi-objective are also used in multimodal. But the idea behind crowding is that I'm going to, instead of using fitness proportional selection, I'll use, say, tournament selection. And in tournament selection, I am going to get a bunch of individuals who might have the same fitness because they're the same Pareto ranking. So what I might want to do then is penalize crowding. So a way to do that is to look at how much empty space is around these contestants of the tournament when they tie. And the one that has more empty space is preferred. So if you happen to be in the same, rank, but you happen to have more individuals around you, then that is going to give you a greater penalty, and you'll then lose that tie. And so you end up penalizing those that have less space around. And so and there are other ways to do crowding as well, but that's the idea, is that you promote space around individuals in your selection operator. So you don't actually modify their fitness, but you break ties for it. And again, we'll see in the multimodal, we'll see some specific concrete examples of crowding algorithms. And then the last type are these population structure methods, which this gets into like MOEA and SGA3. I've already sort of talked about these, where rather than depending upon Pareto ranking to hopefully fill things out uniformly over the Pareto frontier, you create little islands, little neighborhoods, where you do the Pareto ranking just within that neighborhood. And so you now, instead of having one big balloon you're trying to inflate at once, you have a bunch of little balloons, kind of like little party balloons, that all inflate in kind of one direction. And you just make sure that you have enough directions. And then you can do your Pareto ranking or whatever your fitness approach is within those neighborhoods, but you're guaranteed to have enough neighborhoods to begin with because you build that infrastructure up front. So it's a very different way of doing it. These are, you kind of preserve diversity as you go. Here, you build diversity in from the start. Okay, so those are the four major categories of niche preserving approaches, algorithms, and then there are wide amounts of variations of each one of them. So we're going to show a couple concrete ones with multimodal. But that's the basic idea. So again, we're going to see more about each one of these in a little bit. But generally speaking, I'm just trying to set the architecture here is you've got Pareto ranking, which tries to be sucked towards the Pareto frontier, and then these fitness preservation or niching methods try to spread along. Okay. So with that in mind, talk about fitness sharing. Here's an SGA1, the first non-dominated sorting genetic algorithm that used fitness sharing. And this pseudocode is going to look very similar to a normal genetic algorithm, but it just has a slightly different fitness concept and has this fitness sharing. So as with other GAs, we initialize our population and then we evaluate our objective values. So we evaluate our phenotypes. So these are our combinations of traits per individual. And then our fitness concept here is going to be based on dominance. So we look at across all of the individuals we have, who dominates who. So who is better in all objectives relative to another. And that is what's going to give us our notion of fitness, our ranking, our way of ranking these together. Then we do niche counts for our fitness sharing. So for every individual, we're going to then look at how many individuals are within a certain radius of that individual, and we're going to give them a niche count, which is going to divide down their fitness via that fitness sharing. We then can assign a ranked fitness based on their original Pareto rank. So, I said a scaled fitness. So in the case of NSGA1, they used a linear scaling, which allowed you to compress or spread out the scaling. So these were already dense ranks because they use that iterative peeling approach. But then you can spread them out. So you can put a large gap in between each, or you can compress them to have a small gap. And then you take that scaled fitness and you divide it by its count. And so that assigns a shared fitness. And then that will be the thing that's actually driving the selection in the algorithm. So that's what we did. Those are our initial conditions. So we're going to basically do this inside the loop as well. So the way the loop works here, we can do a certain fixed number of generations. An alternative is to make a stopping condition based on Pareto convergence. So what does that look like? Well, we're going to be building up an elite set of non-dominated solutions. You could keep track of who's in that set. And if that set has not changed for like 30 generations continuously, you can say it's probably time to stop. We're probably not going to find any more non-dominated solutions. So the simplest thing, we just go a certain number of generations, but you can do more complex things that have to do with the convergence of the non-dominated set. So then you would use selection via stochastic universal soul sampling, proportional selection. So SUS, it's nice that you don't have to worry so much about drift. So even those that have low fitness get a nice proportion. And then you can do single point crossover. You know, looks like a normal GA here. So all the individuals, regardless of what objectives they're good in, you can put them together, do single point crossover. You can do mutation of that. And then now we're basically repeating what we did before the loop. Evaluate our objective values, evaluate those phenotypes, then assign Pareto ranks based on who now dominates who, compute our niche counts, scale the fitness, and then assign shared fitness to those, and then repeat. And so you can do this approach over and over again, and then hopefully you get movement toward the frontier. And if you get a bunch of individuals clumping together, they get low fitness, and then hopefully some of those get removed, and then you get spreading out around the frontier. So this is basically just a conventional genetic algorithm with a slightly different fitness calculation and niching. So nothing too exotic. Now, in SGA2, it adds crowding. So the maintenance of crowding requires a little bit more bookkeeping, even though it ends up being more efficient, because this compute niche counts, there's a lot hidden there, because it's like an n squared operation where you gotta, figure out who's around everyone else. Crowding, uses tournament selection, and you just have to break ties based on spacing. So you do have to calculate spacing around every individual, but you don't have to do this pairwise thing. Yep.
What's the rationale behind the crowding thing? Because I understand assigning a fitness-based solution, like it helps get a better solution, but having a tiebreaker based on space, how does that help us achieve a better solution?
Well, so the idea, so computationally, crowding is cheaper to calculate, and it's heuristically, it's hopefully does something similar to what fitness sharing does. Because the idea behind it, if I had a Pareto frontier and I had a couple of non-dominated solutions here and a couple of non-dominated solutions down here, these ones have a lot more space around them. So if my tournament selection happened to have selected, say, this one and this one for a tournament, they're both non-dominated. So they both are going to tie in that tournament. But then if I kick it down to now crowding distance, then I see that this individual has a lot less space around it. It's closer to these points. So this individual will lose that, and then it will then end up getting regenerated elsewhere, which will hopefully then lead it to come back up to the frontier and help spread things out along the frontier. So we're trying to penalize clumping along the frontier by using crowding distance, which is sort of a similar thing as trying to be achieved through fitness sharing. Does that make sense?
Yeah, but it also depends on what priority we give to each objective, right? We may want F1 to be more dominant versus F2. It is possible that clustering is desirable.
Well, so we don't weight the objectives at all in any of these multi-objective algorithms. The thought is that that's going to happen afterwards, after we give them a set. And the thought is that if we have a Pareto frontier, this dashed line, and we give them a bunch of individuals that are all up here and then only a couple down here, then we haven't really done a good job, because we haven't shown them that there are individuals that exist in these other areas. And this is sort of a waste of space, because they know that there's at least one individual that has this trade-off. So that's the idea behind crowding, is that we're not trying to say that we don't think that trade-off position is a good one. We're saying we want at least one of them to be there, but we only need one to be there. If there's a bunch there, then let's use that population space and spread them out so we can find additional trade-offs. Does that make sense? Yeah. Okay. All right, so that's the sort of simplest in SGA, in SGA1 with fitness sharing. In SGA2 is the one that is really dominant because it's a little bit faster to use, it works a little bit better, and it uses a crowding-based mechanism instead of sharing. All right, so basically that kind of is a nice way to the evolution of our modern multi-objective algorithms. That one I just showed you in SGA1, it was displaced by the SGA2 crowding, and that's the other nice thing about crowding. Crowding is much more, it's much closer to being parameter free. In crowding, you don't set a minimum niche size. You just penalize based on space. So if you happen to come up in the tournament and you're closer to your neighbors than another one that comes up in the tournament, then you lose. And so you don't have to say ahead of time how big the niches have to be. It just naturally balances the spacing along the frontier. So that was another really nice marketable feature about NSGA2, fewer hyperparameters to worry about. But it only works well for 2 to 3 objectives. So due to this kind of lumpy balloon analogy, which I have no idea if it makes any sense, but it, once you hit multiple objectives, it's just hard to use Pareto ranking enough. So I've mentioned MOEAD. I'm not going to go into how MOEAD works. If you're interested in that, I've posted a video on that. So I'm not asking you by the end of the class, I won't ask you any questions in the exam about MOEAD and how it works. But I just want you to know, as my responsibility to you, sending you off into the world if you ever do multi-objective optimization, is that this is a more modern way. Once you have 3 or more, certainly more objectives, then these approaches based on decomposition, people have figured out how these work. And so when you have multiple objectives, you're going to find NSGA2 everywhere, because a lot of people work with 2 objectives for reasons that we could go into, but and NSGA2 works really well for 2 objectives. But if you really do need to work for 3 objectives or higher, NSGA2 doesn't work very well, but MOEAD does. And so it sort of displaced NSGA2 for higher levels of objectives. Now, the NSGA folks fought back. They brought out NSGA3. It has a diversity approach that was sort of I don't know if it was actually inspired, but it looks like it was inspired by MOEAD. It performs a lot better than NSGA2 at 3 objectives and higher, but it arguably doesn't really perform much better than MOEAD. And both of these are too complex for 2 objectives. Like, it just turns out that for 2 objectives, you don't need all of the extra neighborhood management that these decomposition methods work. So NSGA2 is really elegant for 2 objectives. So even though there are, that's why you say, why don't I just use NSGA3? 3 sounds better than 2. There's not 3, it's a niche. 3's niche is 3 objectives or higher. 2's niche is 2 objectives. And MOEAD's niche is also like 3 objectives or higher. So right now we're seeing competitive exclusion kind of between these methods, trying to duke it out to see who's going to win at the 3 to 4 plus objective case. But really NSGA2 dominates its niche of 2 objectives. People just use NSGA2. It's just that good. Questions about that? The lineup there and of course for single objective, I mean, there's lots of single objective optimizers, but the canonical GA with some slight modifications works great for single objectives. And then there's other approaches as well. For 2 objectives or more, evolutionary algorithms are almost there are some other search methods that you can even find implemented in MATLAB, like Pareto search in MATLAB. They just don't work as well. These evolutionary algorithms really work well for multi-objective problems. Okay. All right, so that's the lineup of your multi-objective. So now I want to use that to pivot to cross into our last unit, I promise, on genetic approaches. This multimodal optimization and distributed genetic algorithms, where we've now learned how to build these amazing niching methods that help spread out along this frontier to help us find these set-based solutions. So we're much better in managing populations. And these set-based solutions, they are like doing lots of single objective optimization at one time. Like the corners of the Pareto frontier. Like if I have a criteria space that has F1 here and F2 here, and I find successfully the Pareto frontier, I have managed to optimize or find a good candidate for the single objective F2 and the single objective F1. I got this flipped, the single objective F2 here and the single objective F1. And I've also done other work as well. So this suggests that maybe we can take what we've learned about multi-objective diversity preservation and somehow improve the things we can do with a single objective. And that's where we're going to be talking about multimodal optimization uses these diversity ideas, and then distributed and parallel genetic algorithms are going to use islanding ideas to bring us back into pure old single mode genetic algorithms that through the power of parallelization, you actually get more bang for the buck than you would get through just putting things in parallel. And so that's how we're going to close this unit. But let's start this unit with multimodal. So I've already talked about how AFPO is an example of how you can use multi-objective methods to maintain diversity to maybe make you better at a single objective. So now we're going to shift this idea to say, well, what if I don't just want the best solution? What if I want to find all the peaks? What if I've got some peaks that, I've got some designs which are equally, perform equally as well as other designs. But I even want to know other designs that are just kind of locally good, even though they aren't necessarily as good as other designs that are available. So a genetic algorithm like the one you implemented for Mini Project 1, it would, if you had multiple peaks of similar fitness, it will eventually coalesce on one peak. There might be some randomness, but it really is driven by finding, one peak and pulling up there. Well, it might be valuable to our stakeholders. If there are alternative peaks of high fitness, then maybe we should let them know about those as well. And that's kind of the idea here, is that we've only been given one objective, but there might be hidden objectives where there's value in knowing all of the different ways that one objective can be maximized. And so when we look at this, it looks a little bit like niches. It looks a little bit like we've got, this is a niche for designs that have 3 wheels. This is a niche for designs that have 4 wheels. And it turns out that if you optimize a 4-wheel design, you can get similar fitness as optimizing a 3-wheel design. That could be one way of viewing this. There's, I think, other perspectives too, but the idea here is that the fact that we want clumping suggests that maybe niching algorithms or diversity preserving algorithms might be something we can leverage. Now, when we look at this, it might remind you a little bit of clonal selection. So in clonal selection, we had a set of antigens that we were developing antibodies for. So we wanted to create, we had a discrete set of antigens, and we wanted to create a discrete set of responses that had high affinity for, each one of those had high affinity for at least one of those antigens. And that was clonalg, the clonal selection algorithm, was one way of doing it. So you start with antigens and you get memory B cells out. Now, one thing you can do with clonalg to make it kind of a basic starter multimodal algorithm is you could get rid of the antigens in the affinity calculation and just create a multimodal fitness function instead. So that, because a multimodal fitness function is going to have discrete peaks, which we can kind of make an analogy to being those discrete antigens. And so you're searching for solutions that are good responses to each one of these peaks. And so the question is, can we stabilize subpopulations across all of these peaks the same way clonalg was able to create little stable subpopulations of antibodies that helped defend against our discrete set of antigen attackers. So, and you can think of this as a stable, as the term we use, polymorphism. It's not being used in the programming sense, but in the kind of ecology sense, or the kind of biological sense, is a polymorphism within a species is the stable, the stable subpopulations of different traits within a species. So there's a coexistence, like, you have red eyes, or you have blue eyes and brown eyes. And, you have a bunch of individuals with blue eyes, a bunch of individuals with brown eyes. So that's a polymorphism. So not everybody converges all to brown eyes or all to blue eyes. So that's kind of the idea here, is we have these, equal fitness phenotypes that Nevertheless, we managed to maintain all of them simultaneously. That's kind of what we're trying to build up here. Turns out CloneAlg is not great at that by itself, because once you replace the antigens with a single fitness function, you have an unknown number of peaks going into it. So we have no way of protecting the number of peaks. In the case of when you have discrete antigens, you know ahead of time you have 8 antigens. When you need, then you know you're looking for 8 different classes of solutions. There's no penalty for clustering on the same peak as well, and there's no reward for spreading out. And peaks that are lower fitness still compete with peaks that are higher fitness. And so even though we would really like to keep this one around, it's going to have lower affinity, lower fitness than these, so it's always at risk of being excluded. So although CloneAlg kind of does a little bit of what we want to do, it doesn't quite fit. So what we're looking for is something that's different than CloneAlg and other single objective GAs that tend to collapse to one peak. As in multi-objective optimization, we're going to try to use diversity preservation to stabilize subpopulations so that we promote diversity along useful directions. So promote diversity in this direction and letting other dimensions converge. So we want both generality in this direction and specificity in this direction. So a good multi-objective optimizer will just have a bunch of individuals right at these individual peaks. So you'll have lots of peak coverage, but then within those peaks, you won't get a lot of spread. You'll get a bunch of individuals just at the tops. That's our goal. That's multimodal. So any questions about our motivations? Multimodal optimization. Yep.
What would be the goal of like finding those smaller peaks as well?
Well, so the idea here is if we have, the thought is we have this resource. So we want to prioritize the higher peaks. So if you say I've got 100 individuals in this algorithm, I would, if you had 3 individuals in the algorithm, I really want those 3 individuals to land on these 3 peaks. But if I happen to have 10, 50, 100, then maybe there's actually some value to finding these lower peaks as well. Going back to that, like these lower peaks might not be that much lower, but our stakeholder, when they look at this design, then they can see that, well, I give up on something that I told you that I wanted. But it turns out there's something really attractive with how this is built that I didn't know that I wanted until I saw them. So by being able to sort of show them this kind of sorted list of top performers and next best performers, then maybe that's valuable to our stakeholder. But if we have a limited population, then we definitely want to prioritize these, not those. Okay. All right. So although most of the literature refers to these as niches, it's kind of a weak analogy. So I'm going to use the term. I'm going to call them niches. I'm going to call them species or whatever. But really, once you go to multimodal objectives, you have one fitness, only one trait that you're really caring about here. And so, the diversity preservation mechanisms actually don't look quite like niching. Like niches really are meant to be different trade-offs. Like you can say, oh, your niche is the slow niche. Well, what else did you have to do in order to be a sloth? Sloths aren't just slow. It's a syndrome of things that is a sloth in order to enable them to have this slow lifestyle. Likewise, a cheetah, there's a syndrome of multiple traits that have to happen simultaneously to build a cheetah. You can't just be fast, right? You've got to be lots of other things to be sustainably fast, and so on and so forth. So those are niches. There is that predatory niche. There is that kind of herbivorous, slow niche. Those are, niches really are about multiple traits. So I'm not comfortable calling these niches because you're only got like one objective. But what it does look like to me, and it fits much better with the math, is as habitat patches. So although we're going to be using genetic algorithms underneath it all, which suggest an evolutionary dynamic, generational dynamics, the diversity preservation mechanisms we're going to look a lot more like animals moving from patch to patch. In other words, it looks a lot more like ducks on a pond. So if you have a pond like this, you go to Kiwanis Park or something like that, and it's got a water area, a bunch of waterfowl come, ducks and coots and everything else, and they're swimming around, and people will show up, and an unknown number of people will show up on the side of the pond at any given day. It could be one person, it could be 10 people, and they're gonna start throwing breadcrumbs. Question?
Isn't this a multi-objective GA then? Because you're doing both diversity as well as the fitness.
The pressure is for both is decomposed into promoting diversity and specificity. But there's only one objective that our stakeholder cares about. When we build the dynamic, we're going to build these two pressures in, but our stakeholder doesn't care about how they did it. All they care about is how well we explored the objective. And so that's why we still view it as a single objective. All right, so each one of these fitness peaks and these multi-modes are basically people that showed up and started throwing breadcrumbs in at these different sides of the pond. And so one of that, the best person, somebody who's there with just a bunch of bread and they just have thrown them in and they've got 10 breadcrumbs every 10 minutes or something like that, or even more than that. Maybe they've got, one breadcrumb a second, 60 breadcrumbs a minute. And they're going to be throwing things in at one side of the pond. But then there's somebody else who just is eating a sandwich and every once in a while throws a piece of bread from their sandwich in. It's much slower. So maybe that person's over here. And then there's others who are sort of in between. And so what you end up getting is the ducks in that pond end up accumulating in front of each one of these people. So if there are 3 people there, there will be 3 clumps of ducks. If there are 2 people there, there will be 2 clumps of ducks. If there are 10 people there, there will be 10 clumps of ducks. And the one who is throwing in the most breadcrumbs will get the most ducks. The one who is throwing in the least breadcrumbs will get the least amount of ducks. This to me, and the dynamics in the math fit this much better too, is much more like what's going on in multimodal diversity preservation. What you're really doing is you're penalizing density so that, but you're doing it in a fitness specific way. So if you get too many individuals at the high density peak, then it ends up becoming better to go to a lower density peak. Just like, even though this person's throwing out a lot of breadcrumbs, if they're throwing out 60 breadcrumbs a minute and then 10 ducks sit in front of them, each duck is only going to get 6 breadcrumbs a minute. So the next duck, if it can get 7 breadcrumbs a minute over here, even though this one, even the absolute number of breadcrumbs is higher, there is a density penalty so that the individual doesn't feel the high quality. They feel the depressed quality. This is fitness sharing. And so then they end up going elsewhere. So this is something that in ecology, we refer to these as suitability functions. And I'm going to pick up with this next time. But this is something that we also use in robotics. It's called the ideal free distribution. And so I'll go into all of these details next time. But the basic idea here is that this idea of frequency-dependent reallocation among habitats is something that we see all throughout natural systems and is well described by this ideal free distribution that has suitability functions which are density dependent. So even though you have a sort of a general suitability for the area, that individual suitability, that individual benefit felt by each duck is divided down by how many other ducks are there. And the last thing I'll mention about this, what's cool about the IFD, which connects to our last unit in a sort of just tangential or sort of coincidental way, is when we think of these social allocations using game theoretic terms, it is both Nash optimal and Pareto optimal. And we'll see why next time. But just putting that out there, we'll pick up here on Thursday. So thanks for struggling with me with the system here. And if you have any questions, feel free to come up. Otherwise, have a good Wednesday.